Mechanical rotational systems. Mechanical rotational systems. So as we discussed in the previous cases, mechanical translational system and mechanical rotational systems, it is also described by three parameters. First one is moment of inertia. Moment of inertia, capital J, moment of inertia of masses. Second one is dashpot, dashpot with rotational friction coefficient, with rotational friction coefficient. Same symbol I am using, B. The third one is torsional spring constant. Torsional spring constant K. Torsional spring constant K. So as we discussed in the previous mathematical translational systems, so here moment of inertia of the masses represented with capital J, and dashpot with rotational friction coefficient B, and torsion spring constant K. The weight of the rotational system is represented by the J. Complete weight of the rotational system is represented by J, and it is assumed that it is concentrated at the center of the body, as we have assumed in the previous method, mechanical translational system. Center of the body, it is assumed to be at center of the body. Elastic deformation of the body is represented by K. Elastic deformation of the body is represented by the spring constant K, and the friction existing in the rotational mechanical system is represented by the dashpot B. So as it is a rotational systems, so we are taking the rotational symbol like this. Same, we are here also we are using Newton's second law. Newton's second law. When a torque is applied to a rotational mechanical systems, then it is opposed by the opposing torques due to moment of inertia, friction, and as well as elasticity of the system. That means sum of torques applied is equal to sum of torques opposed. Applied is equal to opposed torques. That means, let us take this is the total torque applied, then the torque opposed by the moment of inertia of the masses, torque opposed by the dashpot, torque opposed by the spring constant K. So this is the formula we are using in the mechanical rotational system. So similarly, we will see what are the different nomenclature for mechanical rotational system. List of symbols we are using. List of symbols we are using in the mechanical rotational systems are: first one is the theta. It is nothing but angular displacement. Angular displacement in radians. D theta by dt is nothing but angular velocity. This is in radians per second. And d square theta by dt square, it is angular acceleration. Angular acceleration in radians per second square. And T is the total torque applied. Sorry. T is the total torque applied, and J is the moment of inertia. Moment of inertia. in kg meter square per radians, and B is the rotational friction coefficient, rotational frictional coefficient in Newton meter for radians, and K is the stiffness of spring constant, stiffness of spring Newton meter for radians. These are the list of symbols we are using for mechanical rotational system. Now we will discuss one by one in the mechanical rotational system torque balance equation parameters. First one is moment of inertia of masses. Moment of inertia of masses represented with J. So when I am considering an idealized moment of inertia of masses J, then the friction and as well as elasticity are neglected, and here this is my moment of inertia of masses M, and it is assumed to be existing at the center of the body. This is my moment of inertia of the mass. When a torque T is applied on this body, then it will have some displacement, angular displacement theta, and as per the Newton's law, applied torque is equal to opposing torque by the moment of inertia of masses Tj, and this opposing torque is directly proportional to acceleration of the body. So this can be written as Tj is equal to J into d square theta by dt square, acceleration of the body. Equation number 1. Next one is dash pot. Second one is the dash pot. B. So I am considering a dash pot. So this is my dash pot. When a torque T is applied on this dash pot, it undergoes a displacement theta 1, and the torque applied is directly proportional or is equal to the torque opposite by the dash pot. T is equal to TB, and TB is directly proportional to velocity of the angular velocity of the body. So to avoid this proportionality constant, I am writing TB is equal to B into d theta by dt. B into d theta by dt. So this is equation number 2. So here we are having another case, as we discussed in the mechanical translator system. When we are having either side displacement, angular displacement, then it can be considered as, so like this, we are having two sides displacement. This is theta 1 and this is theta 2, and this is the dash pot B. This case, when I am representing with node 1 and node 2, so here with respect to node 1, the torque opposite by the dash pot can be written as B into d by dt of theta 1 minus theta 2. When we are representing with respect to node 2, TB is equal to B into d by dt of theta 2 minus theta 1. These are the two different scenarios generally we face for the dash pot and spring constant when we are solving the problems. And last one, spring constant. Spring constant K can be represented as with the symbol like this, and when a torque T is applied on this, it will undergo certain displacement theta 1, and as per the Newton's law, applied torque is equal to opposite torque by the spring constant K, and Tk is directly proportional to its angular displacement theta 1. To avoid this proportionality constant, I am representing Tk is equal to k into theta 1. So this is the equation number 4. And as we discussed in case of dash pot, when we are having either side displacement for spring constant theta 1 and theta 2, this is node 1 and this is node 2. With respect to node 1, T of k can be written as k into theta 1 minus theta 2, and theta k with respect to node 2 can be written as k into theta 2 minus theta 1. So this is also an important formula for the spring constants in mechanical rotational systems.